We are about to embark on a pretty big unit on acids and bases. So I suppose we should figure out what they are. And maybe you've kind of heard that acids are solutions that contain hydrogen ions and bases are solutions that contain hydroxide. And that's a great way to classify an acid and a base. It works really well for strong acids and bases. And what we're going to find is that by saying strong acid, I just mean that it dissociates fully like a strong electrolyte. Strong electrolyte meaning it dissociates 100% to form ions. Well, now if I say a strong acid, I mean that it's going to dissociate 100%, and one of the ions produced is hydrogen. A strong base would dissociate 100%, and one of the ions produced is hydroxide. So you'll notice that with these two equations that they're listing up on top under the Arrhenius definition, there's just a one-sided arrow because strong acids and bases like these two would really just dissociate 100%, and they don't have a tendency of going in reverse. That maybe a more sophisticated way of looking at acids and bases is with something called the Bronsted-Lowry definition that says acids donate hydrogen and bases accept hydrogen. So you've got a hydrogen donor and a hydrogen acceptor. In that sense, you kind of think of it like this, that yeah, if I have a solution like HCl and it's gonna dissociate to form hydrogen, well, that hydrogen ion is then being produced in the solution. It's donating hydrogen, it's producing hydrogen in the solution. Well, now if I think about a hydrogen acceptor, what do we mean by accepts hydrogen? Well, when I think about a base like my sodium hydroxide or anything that contains hydroxide, well, the hydroxide ion can react with hydrogen and produce water. So by saying it's a hydrogen acceptor, we mean that it can remove hydrogen from the solution. Yeah, I'll even put that there. The acids donate or produce hydrogen, and the bases can accept or remove hydrogen ions from a solution. And so, yeah, like hydroxide is a great base. It can react with hydrogen to form liquid water, which does not ionize. So, yeah, it's a way of accepting hydrogen and removing it from the solution. Now, the other kind of vocab term that we should mention is something called a conjugate acid-base pair. And that's really just two species that differ by just a hydrogen ion. One species is a hydrogen donor, it acts like an acid, and the other pair is a hydrogen acceptor. It acts like a base. And when we say accepting of a proton, a hydrogen ion is a proton. A hydrogen plus one ion is a hydrogen nucleus, and we lost the one electron. And all that's present in a hydrogen nucleus is a proton. So sometimes you might also see these definitions say like a proton donor or a proton acceptor. It really means a hydrogen ion. So check this out. Here's some good examples. When you see these equations now, we're talking about ions in solution, and sometimes you'll see water as part of the reactants. And so I'm going to look at the reactants and products, and we're trying to find two particles that seem to go together. Now, the more you practice these, the more that you'll just kind of be on the lookout for particles that seem to match. So, for example, like this HCl seems to kind of go with the chlorine ion. They both contain chlorine, which then would maybe mean that like the water and the H3O, like they look really similar, don't they? So often you can kind of figure out who's gonna pair with who. And so when they say label an acid and a base, a conjugate acid and a conjugate base. First, we're going to start with the acid and base. The acid and the base will be on the reactant side. These are going to be the reactants. So we're going to look at the HCl, and then we're going to see what does it do? Like, what does he do? Does he gain hydrogen or does he lose hydrogen? And when I see that the HCl turns into just chlorine, I can say, oh, well, he must have been the donor, because on the product side, he's missing his hydrogen. So if the HCl is the hydrogen donor, we say that it's acting like an acid. Well, duh, it's got hydrogen in there, right? So we probably expected that. It's the hydrogen donor. On the other side, it's missing his hydrogen. Well, now I look at water, and I'm going to say, well, what happened to the water on the product side? Oh, he's gained a hydrogen. So the water was the hydrogen acceptor. The water gained the hydrogen. And so we're going to say that water is acting like a base. Oh my gosh, doesn't this feel wrong? Because at one point in your life, I bet somebody told you that water is neutral. Yeah, we'll deal with that. But water is really only neutral when it's pure, when it's all by itself. If I have a solution of something dissolved in the water, water is kind of cool because it can act like an acid or a base. And we just have to look at what happened on the product side. Did the water gain hydrogen like this, or did it lose hydrogen? Okay, so that's kind of how I identify the reactants. The reactants will be the acid and the base. The hydrogen producer, the hydrogen donor, or the hydrogen acceptor. So in a sense, this is kind of what happened, that the HCl gave a hydrogen to the water. And when you think about a water molecule, it's really polar. The bonds are really polar. Oxygen has a really high electronegativity. There's like 2 pairs of electrons sitting on top of the oxygen. So when I think about a water molecule, that oxygen end, and here's the little baby hydrogens, the oxygen end is really negative, and the hydrogens are positive. And so yeah, that negative oxygen end of the water molecule is attracted to positive hydrogen ions. Okay, so now the conjugates are going to be on the product side. So the conjugate acid and conjugate base are the products. And so we kind of ask ourselves, what if this thing were to go in reverse? It's a reversible arrow. What if this thing were to go in reverse? Then what's happening? So if this H3O plus were to go in reverse and turn back into water, what does he have to do? Well, he's got to lose that extra hydrogen, right? So if he's going to lose a hydrogen in the reverse, we would say it's an acid. Well, on the product side, we call them the conjugate acids. Oh. The conjugates on the product side will always be charged. They'll always be the charged ions. Now I say the same thing. What about chlorine? So chlorine is that -1 ion, and what if he wants to go back to the original HCl? What does he have to do? Well, he's got to pick up a hydrogen. He's got to gain a hydrogen. He's got to be the hydrogen acceptor. That's the base. So we're going to call him a conjugate base. And so essentially, if this thing were to go in reverse, then the H3O needs to give that hydrogen back. Oh, interesting. Now, when we say conjugate acid-base pairs, look what kind of happens. That when I have these particles that I said, yeah, I mean, this guy seems to pair with this guy. One of them is an acid in the forward direction. HCl is the hydrogen donor. Well, his partner on the product side is a base. Then if this thing were to go in reverse, the chlorine is going to act like a base and remove hydrogen. The same thing could be said about these guys in the middle. Now we kind of said these guys pair together. Well, going forward, water was the hydrogen acceptor. So it was removing hydrogen from the solution, acting like a base. Well, his buddy on the product side has that extra hydrogen, so to go backwards, he's going to have to give it up and produce hydrogen ion, acting like an acid. So whenever you've got these particles that seem to kind of pair up on the reactant side and the product side, one should end up being the acid and the other's partner should end up being the base, or vice versa. Now I really like what happens in the second one, because when I look at the NH3, I thought bases were supposed to contain hydroxide, that often our bases are things like sodium hydroxide, potassium hydroxide. NH3 doesn't contain hydroxide, and in fact it might almost look more like an acid. It's got hydrogen, but a base is just supposed to produce hydroxide. And as long as there's OH hydroxide on the product side, this solution is gonna be basic. So let's pair these guys up. It probably looks like this NH3 is gonna pair up with the NH4, which probably then means that the water is gonna pair up with the OH. And so I say, okay, like what's happening? If NH3 is gonna turn into NH4, then the NH3 is gaining a hydrogen. It's acting like a hydrogen acceptor. If you're gaining hydrogen, removing hydrogen from the solution, you are acting like a base. But now look at his buddy on the product side. If the NH4 plus 1 were to go in reverse, back to the original NH3, then he's got to give away that extra hydrogen. If NH4 wants to go to NH3, he's got to be a hydrogen donor. So his buddy on the product side, we're going to call the conjugate acid. Often, if you've got an ion that's plus 1 because it's got an extra hydrogen, I bet it can act like an acid. It can be a hydrogen donor. Now look what happens to the water. So the H2O turns into OH. So we lost a hydrogen. So now water is acting like a hydrogen donor. It's acting like an acid. And what we'll find in this study guide is that water is really cool in that it can act like an acid or a base. It just depends on what's mixed with the water. He can be a hydrogen donor and turn into OH, or water can be a hydrogen acceptor and turn into H3O. And again, if it's something that's plus 1 because it's got an extra hydrogen, I bet that H3O can act like an acid. Now, here if I look at the OH hydroxide, and I say, all right, hydroxide, let's say it wants to go in reverse, back to the original water. Well, now he's got to gain hydrogen. He's got to be a hydrogen acceptor, which is a base. We're going to call him the conjugate base. The charged ions are the conjugates. And so you can kind of see that for every acid, the particle on the product side is a base. If this thing were to go in reverse, in one direction it's a hydrogen donor, in the other direction it's a hydrogen acceptor. So there's always acids and bases that pair together depending on the direction that we're moving, forward or reverse. But you'll notice that this OH, which is a typical sign of a base, we did list it as being a base because OH can remove hydrogen from the solution. He would have to get it from this guy. The NH4 would have to give his hydrogen back. Interesting, huh? And look at on the reactant side. It's the water that's now the donor. He's giving his hydrogen to the NH3. So yeah, OH is the sign of a base, but it doesn't have to be that the original solution contained OH. It just has to produce hydroxide, which sometimes the hydroxide might come from water. Wild, right? Now the other ion that we should kind of mention is this guy. H3O is called hydronium. And it's the sign of an acid. It's essentially a hydrogen ion, which is the sign of an acid, right? If we produce hydrogen in solution, yep, it's an acid. But sometimes that hydrogen really does attach itself to a water molecule, just because that oxygen region is pretty negative. So if you either see just a hydrogen ion on the product side, or maybe you'll see that H3O plus 1, either would be the sign of an acidic solution.